Welcome. In this video, we're going to use this graph of a function to explore how secant lines relate to a tangent line. So the first thing we're going to do is use a ruler to make a sketch of the line tangent to this curve at x equals 2. So here's x equals 2, here's this point. So please get some kind of straight edge out and do your best to sketch a tangent line using a ruler. All right, so here's my sketch of the line tangent to F when x equals 2. Yours should be similar. Make sure your line that you sketch touches this point and it has the same slope as the curve, or at least looks as if it has the same slope of this curve at that point. All right, next, we're going to find the average rate of change on the interval from 0 to 2. So that is from x equals 0 here to x equals 2. We're going to find that average rate of change, and then we're going to sketch a secant line connecting those endpoints of that interval. Recall that the average rate of change, that is the average velocity, is the change in our function in our outputs divided by the change in our inputs. So this is f of 2 minus f of 0 minus 2 minus 0, or excuse me, divided by 2 minus 0. Well, what is this function f evaluated when x equals 2? Well, the output is 8. So this is 8 minus, and now when x is 0, the output of this function f is also 0. So this is 8 minus 2 divided by 2, and that's just 4. And actually, to save space, I'm going to go ahead and keep my work lined up. If this confuses you, I would not leave your work lined up. Now I'm going to go ahead and sketch that line. So connecting 0 to 2, or that is x equals 0 to x equals 2, right there. So there in blue is the secant line connecting those 2 points. And what this tells us is the slope of this line, so the average rate of change, the average velocity you might hear it referred to, of this line, the slope of this line is 4. All right, next we're going to do the same thing, but our interval will now be from 1 to 2. So instead of from here to here, our interval starts at 1 and goes to 2. So again, the average rate of change. And I realize I wrote age here instead of average for short, so let me fix that really quick. There we are. So the average rate of change in this case is f of 2 minus f of 1 divided by 2 minus 1. In our denominator, we just have 1. F of 2 is still 8. If you put an input of x equals 2 into this function, you get an output of 8, so that has not changed. F of 1 is 5. So this is just 3. And then I'm going to go ahead and sketch this line again. So there we are. In purple is the secant line connecting the point through x equals 1 to the point through x equals 2. And the slope of this purple secant line is 3. So that's the average rate of change of the curve f between 1 and 2 is 3. Okay, so our interval now for part D is getting even smaller. We want the interval from 2 to 2.5. So that is, I want to start here at 2 and go to 2.5. And on your paper, it's probably easier to see here, this ordered pair. It's covered on mine by these lines. So the average rate of change of our function f between x equals 2 and x equals 2.5. Well, in our denominator, we just get a half, so 0.5. In our numerator, f of 2 is still 8. And as you can see here, this point is 2, 8.75. That's the ordered pair here. It's not very visible anymore. So we have 8 minus 8.75. So that's 3/4 divided by 1/2, or 0.75 divided by 0.5. And that gives you 3/2, or just 1.5. I'm going to go ahead and sketch the secant line connecting these 2 points. All right. So there in pink, we have the secant line connecting the point through x equals 2 and x equals 2.5. Now, before I continue, what are you noticing? Our first interval was this wide, from 0 to 2. Our second interval was from 1 to 2, so this wide, and our current interval from 2 to 2.5. So all these lines, if you notice, they're getting smaller. So our interval along the x-axis is getting smaller. And as that interval gets smaller, notice that these lines end up having a slope that's closer and closer to our orange tangent line. This pink line here, that is the line connecting these two x values, our smallest interval, is in fact the one that shares a slope closest to the slope of our tangent line. Now this brings us to part E. Which secant line comes closest to having the same slope as the tangent line we sketched in part A? Well, the secant line through x equals 2 and x equals 2.5 has the slope most similar to the slope of the tangent line. So a key takeaway: as our interval of inputs here gets smaller and smaller, so we were this long, then we were this long, then we were about that long. As that interval gets smaller, the slope of the secant line approaches the slope of the tangent line. I hope you found this video as exhilarating as a swim on a cold morning.